Welcome to This Explainer. Today, we're ditching those tired old analogies and breaking down the literal, foundational mechanics of how quantum physics really works. If you've ever felt completely overwhelmed by this topic, you are in the perfect place. We're going to rely entirely on what is actually happening to make this whole thing completely accessible.
Here's our roadmap for demystifying the quantum realm. We'll hit the quantum intimidation myth, look at how everything is a wave, tackle the measurement problem, demystify quantum weirdness, and finally answer why call it quantum.
Section 1. The Quantum Intimidation Myth.
You know, when you're just starting out with this stuff, the intimidation factor is honestly huge. I mean, even Nobel Prize winner Richard Feynman, the guy who literally won the award for his work on quantum electrodynamics, famously said, "If you think you understand quantum physics, you don't understand quantum physics." Talk about disheartening, right? If a Nobel laureate doesn't get it, what chance do we have? But actually, as we're going to see, that quote is a little misleading.
The truth is, we actually understand the mechanics exceptionally well. It's arguably the most successful scientific theory ever created. It's the literal foundation of the technologies powering our modern world. We're talking computers, digital cameras, LED screens, lasers, and nuclear power plants. And yeah, you probably wouldn't want to build a nuclear power plant if you didn't absolutely know how it worked.
Section 2. Everything is a wave.
So, to understand how these technologies actually function, we need to completely shift our paradigm. Think about classical physics, Isaac Newton's physics. We picture this clockwork, highly predictable universe made of solid little particles, kind of like tiny billiard balls bouncing around. But quantum physics, it reveals a universe governed by probabilities. Subatomic matter doesn't act like billiard balls at all. Instead, everything is described as abstract mathematical probability waves.
Okay, so here's the absolutely crucial point. What is this wave exactly? Well, a wave function isn't a physical wave like water or sound. It's a purely abstract mathematical map. To figure out where an electron actually is, we have to do some math on this wave, specifically squaring the amplitude. This gives us what's called a probability distribution. So it doesn't tell us exactly where the electron is right now, but it maps out the exact probability of an electron popping up in a specific area when we actually go looking for it.
Which leads us to Section 3, the measurement problem.
Now, a massive, glaring mystery pops up right at the heart of all this math. Let's look at how reality behaves in 3 basic steps. Step 1, you have this spread-out probability wave existing in a hidden realm. Step 2, we put up a barrier which represents the act of measurement. And Step 3, bam, a point-like, localized particle suddenly appears. Whenever we measure an electron, that spread-out mathematical wave seems to just collapse, instantly, into a tiny point. The crazy part? We have absolutely no physics to describe how or why this collapse actually happens. Now, you might be thinking, wait, how do we even know these waves exist if we only ever see particles? Great question. We see this hidden wave behavior in the famous double slit experiment. If you shoot a paintball gun at a wall with 2 slits, you get 2 solid bands of paint on the wall behind it. Simple. But if you fire single electrons at 2 slits, something incredible happens. They travel through those slits as spread out overlapping waves. Where the waves add together, the probability of finding the electron is high, and where they cancel out, the probability is low. As they hit the back wall one by one, they actually build up an interference pattern of stripes. That is something literally only waves can do.
And that brings us right back to our definition of the measurement problem. This unexplained barrier, this bizarre moment where reality transitions from a spread-out wave to a localized particle just because we observe it, is a massive gap in our knowledge. So when Feynman said nobody understands quantum mechanics, this giant, unexplainable hole is exactly what he was talking about.
All right, Section 4, Quantum Weirdness Demystified. Setting that measurement mystery aside for a second, let's look at the broader quantum world. Because once you get that everything acts as a probability wave until it's measured, the greatest hits of quantum weirdness are actually super easy to understand. First up, superposition. You've definitely heard that in quantum physics, things can be in 2 places at once. It sounds like pure magic, but it's just wave math. Superposition literally just means adding waves together. Think of dropping 2 pebbles into a pond and watching those ripples overlap. Mathematically, superimposing 2 wave functions allows an electron to have a probability of being in multiple places simultaneously. No magic involved, just overlapping probabilities.
Next up is quantum entanglement. And again, let's ditch the sci-fi explanations.
Entanglement is just what happens when two waves meet, interfere, and link up. Once they mix, they become mathematically described by one single inextricably linked wave function. This just means that measuring the state of one particle instantly correlates with the measurement of the other, simply because they share the exact same underlying math.
Now, what is truly mind-bending here is the scale. We are talking billions of miles. This non-local correlation between entangled particles persists even if they're separated by billions of miles across the universe. This fact made Albert Einstein deeply uncomfortable. He honestly hated it because it had the whiff of faster-than-light communication, totally messing with his theory of relativity. Now, you can't actually use it to send information since the measurement results are totally random, but that underlying link, it is undeniably there.
Let's look at another weird one, quantum tunneling. Because a wave function isn't a hard physical object but just a probability distribution, when it hits a narrow barrier, the wave decays exponentially, sure, but it can actually survive on the other side. This gives a particle a mathematical probability to just pass through solid walls. And the crazy thing? This is the literal reason you are alive today. Protons normally repel each other, but thanks to quantum tunneling, they have a tiny probability of passing through that repulsive barrier and fusing together anyway. That fusion is exactly what makes the sun shine, giving us the energy for almost all life on Earth.
Then we have the famous Heisenberg uncertainty principle, which basically says you can't know everything precisely. Once again, this is just a natural trade-off of wave math. If you want to know a particle's exact momentum, you need a perfect sine wave with a single wavelength. But a perfect sine wave stretches out forever, meaning the particle's position has an equal probability of being literally anywhere in the universe. On the flip side, if you build a wave that gives you a completely definite single position, you have to mash together so many different wavelengths that the momentum becomes completely uncertain. So it's not a limit of our measuring tools at all, it's just a fundamental mathematical property of the universe.
Moving on to our final section, Section 5, why call it quantum?
So with all this talk about waves, math, and probabilities, you're probably wondering, where does the word quantum actually come from? What does it mean? Well, a quanta is just a specific discrete packet or chunk of something. Like how you might grab a specific packet of sugar for your coffee, in physics, you can have a discrete packet of energy.
To picture how this applies, think of a guitar string that's tied down at both ends. Because the ends are completely fixed, that string can only vibrate in specific, restricted ways. It can only have certain exact wavelengths. The exact same thing happens to an electron trapped inside an atom. The electron wave is constrained by the atom itself, meaning it becomes quantized. It can only vibrate at specific, restricted energy levels. Short wavelengths give you high energy, and long wavelengths give you low energy.
So, when an electron jumps from a high-energy short wavelength down to a lower-energy long wavelength, it has to release that leftover energy. It emits this light in a discrete, quantized packet called a photon. And because the electron can only jump between those highly specific, restricted wavelengths, it only emits highly specific colors of light. This creates the exact barcode of emitted light we see in atomic spectra. The light is literally quantized into chunks. So to wrap up our explainer today, quantum physics is perfectly predictive, and it is the literal foundation of our modern technological world. Everything is mathematically driven by these wave functions which naturally, beautifully explain superposition, entanglement, tunneling, and quantized energy. Yet despite all of this, the whole thing is built around a massive, unexplained hole called the measurement problem. So, I want to leave you with this. Will we ever discover the actual physics of how a mathematical wave collapses into a physical particle? Or is the truest nature of reality destined to forever remain just outside human comprehension? Thanks for exploring the true mechanics of the quantum realm with me today.